Joining us next on stage is Prahlad Venkatapuram. Prahlad is a Senior Director of Engineering at Meta. Sounds like a hyperscale. Prahlad has been in the semiconductor industry for over 3 decades and leads the infrastructure silicon development at Meta, spanning across various domains such as video transcoding, AI, ML, and interconnect technologies. Today, Prahlad will talk about building data center scale SoCs using RISC-V at Meta. Please welcome Prahlad to the stage.
Good morning. I hope everybody is awake. I know we all started early, but I started developing in-house silicon at Meta approximately 5.5 years ago. I was given the opportunity to start the team, build the team, and develop silicon there. Today, we'll be talking about building data center scale SoCs using RISC-V at Meta. We have successfully deployed in several products, and they are in production, working production workloads. So to start off with, what is the need for a processor core in the accelerators, within the accelerators that we are developing, and why we chose RISC-V? And then what are the example use cases where we successfully deployed the RISC-V core, where billions of users are being supported today? And what were the challenges that we had while we were developing these RISC-V cores? It's more than challenges, it was still evolving. A lot of work on the RISC-V was evolving approximately 4 years ago, and those are the aspects that I would like to cover. And then call to action is more of a request to the community to help us go to the next level. So coming back to the need for a processor core, so why do we need it? Acceleration in data center has become extremely important for us. There are some business critical metric we cannot really optimize using the basic CPUs that are available today. And the metric that we are really looking for is power efficiency, performance, and we want absolute low latency on the server. So these are some of the few examples that are the motivating factors for us to choose a processor core. And we expect these accelerators need to be absolutely flexible, support variety of workloads within a given class. And then the second is we also should be resilient with the architecture so that it is extensible to new categories of workloads in the domain that do come up in its lifetime. So anytime we design something or deploy something, we expect it to be there for at least 3 to 4 years. So there should be some resiliency in the architecture. And the third aspect is obviously the programmability that allows flexibility in composition and control. So essentially, we want to put software in charge of how we simulate or stimulate our hardware resources and how they are managed, used, and sequenced to accomplish the end task. So now coming back to why RISC-V, right? So before we even started looking at RISC-V, we had 3 major architectural requirements at the beginning of the project. One of the key things is 64-bit addressing. This is to support large address space and memory, because we do have large models in the AI space, especially for server class applications. And then the second one is vector and SIMD capabilities within the core. And then the last one is ability to add custom instructions. These were the 3 things that were absolutely required for us. And having heard the previous presentation and the initial presentation, it is very apparent that RISC-V does offer these features today, right? It's an open architecture. It is strong support and acceptance in the community. There are multiple providers of IP. And there's also a growing ecosystem that we have we are seeing over the last 4 or 5 years. At least we have been seeing. And has a very capable standard vector extension today. So, and then there is also provision for adding custom instructions from the start because of the reserved opcode space that has been accommodated from day one into the architecture. So now coming back to why customize the core? Because obviously there are several reasons why we want to customize this core for our specific application. We have been talking about domain. So for performance reasons, we need to build special hardware for common operations like matrix multiplications, realizing nonlinear functions, and data transfer layout manipulations. So these are the 3 areas that we have addressed and essentially created the proper instructions that can essentially be combined and realize the operators that are needed to accelerate some of our AI inference applications. These operations are essentially composed. That's what I meant by combining. And if you look at what is not available today, but what was not available at the time we started, that these operations are not supported as part of the standard RISC-V instruction set architecture. So, and we had to essentially develop these as part of the core. So ideally, we would like to do this in-house, all these applications, because these are very specific to our workload needs. We understand what type of operators are required based on the profiling that we do on the workloads. So that way, we maintain control over proprietary IP and innovations. And then we also minimize external interactions. That means we develop a lot faster because we have access to our workload nature, right? And modify things quickly in response in changes to the requirements. So along the way, while you're developing also, we do see that the workloads themselves evolve. And then we want to be resilient to accepting changes in the later stage of the project also. And that gives us the ability. So in terms of where we deployed these, right? So we have deployed in first silicon that way we deployed the RISC-V core is in our Meta's scalable video processor. So this is our first in-house silicon for video processing. This is the first server-class video processor that we have developed. There are a lot of video processors that are in the industry, in the consumer space today, but this is a different level of performance that we wanted to target. More than performance is providing the best video quality at the lowest bit rate. So that means we want to use all the tools that are possible within the codec standards and come up with a solution. So today, we do have this chip. It is deployed onto the servers. It is serving 100% of our video uploads on the server today. That means what we were doing on the CPUs earlier, we probably would have replaced 85% of them with these accelerators. So we use only 15% of those CPUs to realize these workloads with this accelerator in place on the server. And this is like a 9x throughput for H.264 videos over libx running on typical CPUs as a software. And then they also have a 50x throughput for VP9 videos. And then it's just 9 watts per chip, 12 watts per M.2 module. M.2 module is what we use on our servers to plug into a PCIe compliant device. So if you look at what is the purpose of this control processor, this RISC processor essentially does very complex function. It does utilize the full capacity of that 4K 60 video capability and split into multiple sessions of smaller resolutions at frame boundary. So it's all different sessions. It also realizes sequence null, picture null at that level, and then accelerator essentially takes care at the slice null level, right? So all those scheduling between all the functions within the video transcoder core, as well as realizing some of the video transcode function itself is all done on the RISC-V core. And this is the one that is really creating and hardware abstraction layer for our API, for all our video applications running for Facebook, Instagram, WhatsApp, Messenger, or whatever. Another area that we have extensively used RISC-V is Meta's training and inference accelerator. So our first in-house silicon for accelerating deep learning recommendation models in the data center, we have used processing elements, which is an 8x8 grid. Each processing element has two RISC-V cores. One is a scalar core, other is a vector core. So we do use those along with the fixed functions within the core. So if you look at how we have architected that, is we do have a scalar core, we do have a vector core, and then it's essentially communicating with the command processor, and then it is working in conjunction with some of the fixed functions that are shown in green that we have developed in-house. That is the IP, the technology that we have developed. In addition to that, we also use the vector instructions that are already part of the processor B, and then realize all our workloads and get the performance that we need today. And we heavily customized this architecture. And some of the areas that we have addressed in the process of customization is creating custom interfaces to connect to the external hardware. And then the second one is custom instructions itself to control external hardware. And the third is custom registers to store and pass control information. And the last one is custom exceptions to check validity of control information. So in addition to that, obviously, we have a full-fledged interrupt timer and debug subsystem that we have created to get visibility into the cores. And this subsystem is essentially shared between the two cores, processor A as well as processor B. So along the way, what we have done is we have clearly identified that RISC-V is the way to go for us moving forward for all the products that we have in the roadmap that will be addressing not only next-generation video transcoders, but also next-generation inference accelerators and training chips. And there, we have standardized this RISC-based control system, and then we made it scalable so that any IP that we develop for any domain is adaptable, and it just connects on the NOC. So there is a NOC that is sitting in there, and the IP just connects to that NOC, and essentially we use RISC-V. So if you look at it, based on the multi-core RISC-V cluster, we created a control RISC-V subsystem. The second one is RISC-V specifically for security, and the third is chip resource management. So these are all the areas we covered, and we created a template. And then we will be extensively using this. And we have clearly adopted Zephyr as a real-time operating system of our choice, and we augmented with in-house and vendor-specific extensions. So while we were developing these, I wouldn't say typically challenges, but while the specs have been evolving, these were some of the areas that we found that development should have happened sooner, or specs would have been ratified sooner in certain cases. So first one is the lack of extensive customization capability in existing IP offerings. So how do we have the tools that automatically take a high-level description of the type of custom instructions that we want to realize, and then automatically an RTL gets generated? How associated simulator tools get generated, or software tools get generated, associated compilers that seamlessly invoke whatever custom instructions we have put in are seen as part of the compile operation. So these were all the challenges that we saw in the beginning. But I think obviously the spec is evolving, and it is addressing a lot of our issues today. And the second one is unfinished ratification work on important extensions, like vector extension, and for example, having a standard trace interface for the core. These are the areas that we saw, there were some shortfalls, but these are improving over time. And then the last one is a lack of interoperability between offerings from different vendors, right? The processor core and the trace encoder. So we would like to obviously see this area evolve better and then eventually meet our requirements. So, and essentially lack of complete and sophisticated debug environment, something very similar to the core site that ARM is offering today. And from the software perspective, as you all know, RISC-V did start off its development using mainly for embedded applications, right? And then over the years, in the last 3-4 years, it has evolved, and now slowly it has started supporting server-class applications. And once we say server-class applications, we need solid support for large memory models in the RISC-V specifications. So large memory models obviously can optimize performance for data center applications, right? And then in addition to that, it was also very difficult to write portable code using the medium memory model, right? Which makes no distinction between code and data segments, spanning at most 4 GB of address space. And the second one is the LLVM support for RISC-V is improving. We have seen it improve over the last 3-4 years, but we would still like to see some of the areas that we collectively work towards, like LLVM backend maturity, like auto vectorization capability, and overall quality of generated code. And then the libraries such as libc, compiler are not mature and robust as for other architectures, and some LLVM sanitizers either not available or robust enough for RISC-V today. In terms of the support, obviously one of the areas that we are looking for, or the community to help us, is on the matrix operations, which are very important for us in the kernel development for our AI workloads. We would like the RISC-V, RISC-V has very capable vector extension, as we all know, but there are no standards existing in terms of the extensions for matrices. There is active work going on. We do understand, when we have been working very closely, and we have been closely monitoring. And then we also know that RISC-V AI/ML SIG is also making tremendous progress on this front. And then we also would like some proposals by multiple different vendors, like Stream Computing, TED Semiconductor, and others. So it is imperative to accelerate the definition and ratification of the matrix extension for us. And similar to this, also some of the aspects on the ecosystem, mainly the software aspect of the ecosystem, where we would like more and more libraries being developed, especially to address the space like linear algebra, CMSIS equivalent, and some of the signal processing kernels. So these are all the areas that we are looking to the community to help us so that we go to the next level. And then in terms of the hardware ecosystem also, peripheral IP tested with the RISC-V cores, peripheral IP that is recommended and guaranteed to operate and coexist in a system. And then the last one is obviously the standardization. Essentially, various vendors today, they do provide excellent capabilities. They all provide very high performance cores, addressing all the way from the consumer space to high performance compute. But again, there are various vendors that are providing different, and we just want it to be a little bit standardized, right? And then, so providing a standard way especially to specify the custom extensions. And in terms of, and obviously once the standardization is in place, it's a highway to standardize extensions. It gives users the power of choice. It enables portability across different generations and offerings. And then it paves the way for turning custom extensions into almost standard extensions. essentially supported by all vendors and uniformly and seamlessly introduced to compiler and software. So we don't have to start developing custom compilers specific to each core that every individual develops. And then this fuels and accelerates innovation. That's what we feel. In summary, we clearly understand that RISC-V is a powerful and open instruction set architecture. We have clearly embraced, we have built and deployed multiple RISC-V based SoCs in our data centers. We continue deploying those. It enables constructing and deploying SoCs and accelerators at data center scale. We are fully convinced, right? And still has a lot of opportunities for improvement, as I talked before. Some of the software side, some of the libraries that we need to develop and tooling support, and then obviously the interoperability of cores and components. And then would like to rally a community around a few of these priorities like matrix support, ecosystem enhancements, and a standard way for describing custom extensions. Thank you.